Hi everyone. Let's program a simple effect that simulates looking at the scene through rapid glass, also known as fluted glass. It's a straightforward algorithm based on a combination of a few basic principles. So let's get started. Okay, let's start. This time it's not about any transition between scenes, so we can get by with a single background image. I'll create the usual scene with a sprite 2D node and then apply a new shader material to its material property. So right-clicking the scenes folder, create a new scene. It's a 2D scene and let's call it fluted glass. Okay, now I'm dragging the usual screenshot found in JPEG into the 2D editor. The sprite 2D node was automatically created, and in the inspector, let's go to offset and cancel centered. Let's expand transform and reset position to 0, 0. Scrolling down to the material section and opening material, where sorry, I'll add a new shader material to the material property, click it, and create a new shader called Fluted Glass.gd shader. Type shader, mode canvas item, and the folder is, as usual, shaders. Create, and clicking again, open it in the shader editor. Alright, and as usual, we'll improve the readability of the shader code by deleting everything that won't be needed. That way, only the fragment function will remain. So deleting vertex and deleting white. Ctrl S to save. Okay, and now we can move on to implementing the fragment function. For the effect I'm about to create, we will divide the image into a predefined number of columns. It means that there is no need to recalculate the aspect ratio or shift the coordinate origin to the center. We'll simply work with the UV coordinates as they are. So I'm deleting the comment and writing the single line. Simple line back to UV is just the internal UV. Okay, to determine which column the current pixel belongs to, we assign a unique ID to each column. For that, we need to know their total number, so I'll define it as the first uniform parameter. Uniform float count with a hint range, and let's start with 10 flutes, and the range would go from 1 to, for instance, 20, and the step, of course, is 1. No fractional flutes, of course. Okay, and now we can define a variable called flute ID in the fragment function. Flute ID is floor of UVX times our parameter flute count. Okay, as we know, this type of glass isn't made of that columns. Isn't made of flat columns, but rounded ones, which cause a corresponding distortion of the image. To control this deformation, we introduce a second uniform parameter called compress ratio, right here. Uniform float compress ratio with another hint range, and let's start with 1.2 as the ratio, and the range I will set to from 0.1 to 10 with the step to 2, with the step point 0.1. Okay, using it, we then add a variable named flute size. So I'm back in the fragment function and writing float flute size is compress ratio divided by flute count. Okay, with the calculations so far, we can now determine the local horizontal coordinate needed for the rest of the algorithm. Let's call it flute x. And the calculation is simple. Float fluid x equals UVX minus fluid ID divided by fluid count, and let's multiply the result by fluid count again. Okay, so this remaps the global UV coordinate, this one, into a local 0 to 1 interval within each column. Now we can move on to the main part of our algorithm, deforming the image using a smooth curve. If I switch to Desmos, I can quickly show how I arrived at this function. So we already know this very handy tool, which you can find at the URL desmos.com/calculator. Alright, let's write simply sine x. This is the graph of the sine function, which intersects the x-axis at multiples of pi, like 3.13 and twice pi, and so on. To get zero values at x, 1, 2, 3, and so on, I'll multiply the argument by pi. So x times pi. Now we can see it how it crosses at 0, 1, 2, -1, and so on. Now, if I subtract this expression from 1, 1 minus, and move the graph a little bit, we can see that I got a function that reaches a value of 1 at the edges of the 0 to 1 interval, smoothly dips towards the center, and then rises again. That's exactly what we need to simulate fluted glass. Very well, let's switch back to Godot here. And I'll write the same formula multiplied by a parameter called refraction to allow further adjustment and store the result in a variable named compression. So let's add the parameter first, a uniform float refraction with a hint range, and let's start at 1.5. Okay, and I'll set the range from 0.1 to 5 with a step 0.01. All right, and now the mentioned compression variable in the fragment function. So I'm adding another row, float compression equals 1 minus sine fluid x times pi, just like I did in Desmos, and multiplying the result by the refraction parameter. Okay, now we can place the individual columns into the final image. We want them to overlap slightly to hide the sharp transitions between them, so I'll add a uniform parameter called edge overlap. Uniform float edge overlap with a hint range, and I'll set the overlap to 0.2. And the range goes from 0 to 1 with the step 0.01, and I'll use it to calculate the starting position of the current column right here. Float fluid start equals fluid ID times fluid fluid size minus edge overlap, our parameter, divided by fluid count, I think. Yeah, definitely this one. Okay, the result of these calculations is a new set of UV coordinates, which we'll use to sample the corresponding pixel from the original image. Let's write them. Vector 2, and call it fluid UV, equals vector 2, and now fluid start plus our compression value times fluid size, and the second one is simply UV. Why? Because we are not doing any deformations across the vertical axis. Alright, and finally, as I said, let's create the color. Vector for color RGBA format equals simply a texture function applied on our texture, and the coordinates are flute UV, the deformed one. And finally, let's display that pixel. Color, the output is simply color, our variable, wait for it. Okay. It seems that something is not entirely correct here, and when I looked, of course, flute size is wrong. It should be flute start. Here, let's fix that. Wait for it again. Now, not a bad result, right? But I think something is still missing. The transitions between the columns are too smooth, as we can see if I zoom in, and it's barely noticeable that we are looking through glass. So we'll improve this by introducing one last parameter called edge brightness. Uniform float edge brightness with a hint range, and I'll start at 0.2, and then the range again from 0 to 1 with the step point 0,1. All right, and now let's use it. First, I'll highlight the left edge of each column in white with some transparency. The smooth step and the mix functions will help me with that. Let's do it here before the final assignment to the output color. So float left edge is, as I said, smooth step of with the edges 0.1 and 0, and let's apply it on flute X. Okay, and now I will mix it into our already calculated color. So color equals mix of color, and now vector 4, vector 3, 1, the white color, and the alpha value, it will be driven by the variable left edge, by the smooth step, and the third argument would be left edge times our edge brightness. Okay, yeah, definitely an improvement. And I'll do something similar for the right edge, and this time I'll use a black color. This gives the final effect a more convincing 3D look. So I think I'll just copy and paste these two lines and rename the first one to right edge, and the smooth step this time goes from 0.9 to 1, and again is applied on flute X. And let's mix in the right edge right here, and let's use, as I said, the black color. So right edge and right edge times edge brightness. Okay, and I think now we are really done. Let's just expand this to see more of the image, and we can try tweaking the parameters and observe how they affect the overall appearance. So for example, flute count increasing, now it's 20, now it's just 1, 2, 3, 4, 5, yeah. Let's get back to 10 and fix the compress ratio, and now we can see the smooth refraction. Well, move this slider. As for the real refraction, we can change it right here, and the edge overlap, again, it affects how the columns overlap each other. And as for the edge brightness, now it's brighter, now it's darker. Yeah, definitely many ways to customize that. Thank you very much for watching. This time it was a bit faster, so we could take a break from the more complex algorithms I covered in previous tutorials. And perhaps the simpler the effect, the more practical uses it has in different types of games. So I'll try to showcase more of those on this channel in the future. And for now, take care, good luck with your projects, and I'll see you in the next video.